So, my talk is about automated memory analysis based on types. And this is jointly with Nicole and Xavier. So why do we need automated memory analysis? The first reason is memory safety. Memory safety errors are still the more pervasive source of vulnerability every year. And we have here two reports, one from Microsoft, one from Google, and both said around 70%. Oh,
wait.
Oh,
Okay.
It's fine.
Okay, now we're good enough.
Okay. So both say that around 70% of the vulnerabilities they find are memory safety errors. The second reason are the need to find structural invariants on memory, and especially in low-level system programs. And this was already true in the 80s. For instance, in the proof of the UCLA Unix security kernel, they said that much of the kernel code was directed at maintaining data structure invariants. And it's still true today in the comprehensive report of the STL4 verification effort. They said that there were 4 main categories of invariants in our proofs: low-level memory invariants, typing invariants, data structure invariants, and algorithmic invariants. And 80% of the effort that they spent to prove the STL4 kernel went into establishing these invariants. So both of the reasons, memory safety and the need to find structural invariants, are reasons why we need practical and automated memory analysis for low-level language. Now, there are two families of automated memory analysis, two broad families. The first are pointer analysis, like Stinsgard and Anderson's skill of analysis. They are very efficient. They are easy to automate. They are practically fully automated, but they are too imprecise to prove memory safety or to prove any structural invariant. On the other hand, you have shape analysis, like analysis based on separation logic and TVLA-based analysis, and they are not as efficient as pointer analysis. They require some setup to be launched, but they can prove memory safety and they can prove very strong structural invariance of the memory. And what we would like to achieve is a kind of middle ground between both of these approaches. Analysis which will be efficient, maybe not as efficient as the pointer analysis, but still quite efficient, which will be quite automated. We can have some low-level amount of parameterization, but it should be light. But on the other hand, we will be able to prove memory safety and to prove structural invariance, even if this structural invariance will not be as strong as a structural invariance that we can prove using a shape analysis. And moreover, we would like to be able to do that on both low-level C code and also on machine code, an executable code. So our approach to do that is the abstract interpretation based on types. So what we will do is that on the one hand, we will rely on type to gain some precision, and on the other hand, we will also establish and verify type safety. And by type safety, this implies memory safety. And we will do that using a dedicated type system, and the purpose of this type system is to be used in the abstract interpretation. So you had existing works which combine types and static analysis before, but often they are either static analysis that assume that type safety is already present, or you have a syntactic and decidable type inference algorithms, and they are not sufficiently precise for system code. For instance, if you want to be decidable, you have to give up on dependent types, and dependent types are very important to prove the safety of system program. So this will be a short overview of how our technique looks like. So we start from a standard semantics for machine code, where we have here a memory heap, and here we have some variables which can be kind of machine registers. And we have a program which points to a first cell in memory, and we can perform memory reads and memory writes. Here we read the value n at value p, so we read 100c, and then we can write to memory. Okay, so this is really standard. On top of that, we have types, and what do types do is that they are used to tag the memory and the types of the variable. For instance, we define two types here. The first type is the data. The data can be any word with the restriction that the value must be smaller than 10. So this is a dependent type. And the other type is a node. So node is a record, and the first field must be a pointer to a node. And the node .0 here means that it must be a pointer to the first offset, to the beginning of a node, so the offset 0 of the node. And the second field must be the data. So this is a linked list of values that should be smaller than 10. And we use this type to type the data. So we say here that the first 8 bytes here should be a node, the last 8 bytes should be a node, and the middle 4 bytes here should be just a word. And we also tag or assign types to the variables. So we say here that P should be a pointer to the beginning of a node, and N can be any random word. And starting from this initial state, we can verify that each operation here is well typed, meaning that it preserves the structural invariants that we will detail later. Now, so this types allows to describe some structural invariants on the memory. And what our abstract domain does is just consider this part. So this is just the mapping of variables to types. And we will use continuously the invariants that all the states that we manipulate are well typed. And we will verify that this is indeed the case in every assignment that we do. So this is our base domain, but it's not very efficient by itself. Where it really shines is when it is combined with other abstract domains, and in particular with numerical abstraction. So we can have a numerical abstraction that attach numerical constraints to programs. So here, for instance, we know that P is assigned a value pi, and pi is different from 0. So this allows to verify the safety of this memory reference. And we can also attach memory numerical constraints to some heap values. And this is how our full abstract domain works. It's a combination of all of these analyses. So now I can present what's the summary of all the contributions that we had. So first we present type concrete semantics, so structural invariants that can be expressed by types, then our abstract domain. And then we had an interesting set of experiments. The first is that we took existing shape benchmarks for C programs. We verified memory safety of them and light structural invariants if we could prove them. And we did the same with the same benchmark, but combined to binary. And the second experiment that we did is that we took a full commercial microkernel and we verified interesting security properties like absence of privilege escalation and absence of runtime error directly from its executable. So let's move on to explaining how our type semantic works. So we have lots of types. We have words which can be any value. We have named types. We have pointer types, record types, array types, and refinement types. We say type with a predicate. And we have a very important notion here, which is a type with an offset. So T.O means that we have a type, and we are writing the byte number O in the type. And we have definitions which are just bindings from name to type. So these are the definitions that I gave you earlier. Now we have a notion of heaps and labeling. So a heap is just a mapping from address to values. And what's important is that we want to deal with low-level programs. So we want to perform byte-level reasoning. So when I say that I load a word at one address 1000, it means that I will load the first byte at address 1000, and the second byte at 1001, and so on. And we want to do the same for labeling. So labeling is the assignment of address to types. And here I say that the first 8 bytes from 1000 to 1007 are of type node. And what this means is that the first byte is of type node 0.0, and the second byte is of type node 0.1, and so on. And why it is important is that it will enable us to perform to verify the safety of pointer arithmetics. So here, if you have a pointer to a specific offset in a type, and we increment this pointer by a value I, then we know that if we are still inside the bound of the type, we will now have a pointer to the different of the new set in the type. Now, what does it mean for 8 contiguous bytes to be of type node? It means that the last 8 bytes, the last 4 bytes will contain a data, and the first 4 bytes will contain a pointer to a node. So one other way to say this is to say that the byte of type node 0.7 contains the value of data 0.3. So we have a kind of ordering between the types, which is a containment ordering. And why do we use this? Is that we will use this as a kind of subtyping. Basically, we can say that if we have a pointer to a node 0.7, then it can be translated into a pointer to a data 0.3. So we are subtyping in our type system. Now we can continue and say that the data 0.3 is also the first part of the word, and that everything is a byte. So we have a complete lattice, and this lattice will be used to perform join operations and inclusion that are the most important operations in an abstract interpretation. And moreover, this structure has the shape of a tree. And it's important because this will enable us to have rules about aliasing. And in particular, if we have 2 pointers with point to types which are in different parts of the tree, then we know that they will not alias. For instance, a pointer means if you have a pointer to a node 7 and a pointer to a data 0.2, then we know that both pointer will not alias. And a sort of aliasing, of course, is very important if we want to perform a memory analysis. So up to now, we use types only to tag address of memory, but we have another interpretation of type, which is a type which can be used to describe a set of values. So for instance, the word it can be any value. A type with a predicate is any value that match the predicate. And a pointer type is the set of addresses that are tagged with that type. So for instance, the type not.0 star, which with self different from 0, means that not.0 star means the address 1000, start of the node, 100C, which is the start of the second node, and the value 0. And the value 0 can be removed with the predicate self different from 0. So this is a non-null pointer type. And now we have everything in place to explain what our structural invariance on the heap looks like. And this is all in this definition of what's a well-typed state. Basically, what it says is that if you have an address of type T, it should contain a value corresponding to its type. So for instance, this is well-typed because it contains here a correct pointer and here a value smaller than 10. And this is ill-typed. Why? Because this contains a value which should be the beginning of a node, but here it points to the middle of the node. And here this is incorrect also because it should contain a value smaller than 10, and here we have 22. So these are not well-typed values, they are ill-typed states. And similarly, we have constraints on the value of variables. For example, this is correct, and this is also incorrect because it should be a pointer to the beginning of a node, and it actually contains a value which points inside of a node. So this is also incorrect. And with that, we described completely what kind of structural invariance we can describe using our type system. So now our subdomain is simply a mapping from variable to types. And basically what is described is that we take the set of all the well-typed states whose variables can be typed using the environment, and we just erase the types. So for instance, here I took a new definition of 2 subtypes of type data, type foo and type bar, and we have P and Q, which are pointers to foo, and R, which is a pointer to bar. And basically, what is described is a set of all the values where P and Q may or may not alias, but R must not alias with P and Q. because this is correct, this is correct, this is incorrect. And also, the contents of P, Q, and R must be to some words which must be smaller than 10. And these are the only constraints that this type system, the spatial type system describes. Okay, so as we said, this base analysis by itself is not very important, but it's not very precise, but it works very well when combined with numerical abstractions. So here we assign some symbols to variables, and we have numerical constraints on these variables. And when we perform the analysis of the statement assume P different from 0, we can learn that the variable is different from 0. And this allows to check the safety of this statement. We know that this statement will preserve the structural invariance of our program. So this is the correct program. Now, often this is not sufficient. For instance, here, if I now try to assume that the value pointed by P is different from 0, I will not learn anything from this statement by default. So what I need to do to be able to learn something from this is to add this, what we call these points to predicates. Those points to predicates, this means that at the address P, we have the contents at P is alpha and beta. So alpha at P is beta at P plus 4. And now we can learn that the contents of this if cell is different from 0. And now I can prove the safety of this statement because I know that I will not be performing any null pointer dereference. And we can learn a lot of stuff about the memory. We have some interesting pragmatic extensions. For instance, I've kind of simplified the analysis. In the free analysis, we have things like array type and kind of global parameters. So, for instance, this describes a structure which contains the size of an array and an array of that size, and you can link both of them using this global parameters, which is the current class. And then we can have pointers. So this says that I have a pointer with a variable offset, and this offset must be smaller than the size of the array. So this is also important when we want to perform array analysis, so our analysis is not limited to linked data structures. Okay, so now I move on to the experiments. First, a quick word about the implementation. We have implemented both every of these abstract domains in the Codex library for abstract interpretation, and we implemented two static analyses, one for C using pharmacy, and one for binary code using VMCAI platform. And so we implemented on the benchmarks, first the shape benchmark, and here the goal was to verify memory safety in the version of complex or structural invariants in complex code that manipulate that make heavy use of data structure manipulation. And the second was on a larger scale benchmark, which is a full industrial embedded microkernel. And now the goal was to verify can we prove sufficient number of structural invariants that able to prove the safety of the kernel, the entire kernel. And for each of the benchmark, we evaluated the performance in terms of the time of taken base analysis, the precision, and the ease of setup and automation that we measure in terms of lives of annotation. So for the shape benchmarks, this is an excerpt of the table. Here we have a number of what we call generated types. So this corresponds to the types that already exist in the program, so say types that we can just copy and paste as a basis for our types. Then these are the number of lines that we had to manually edit. And these are the preconditions of the program. So in most benchmark, you have to assume that the initial pointer taken as argument to the function was not done. And we can see here that the ratio between the number of annotations and the number of lines of code is quite good. And here we have the number of benchmarks that we verified. So we did not verify all of them, but we can verify 30 out of 34 of them without modification. So it was quite good. And we can see that the points two predicates are very important because without them, we could prove only 13 or a very low number of these benchmarks. And finally, we observe that we can prove as well the C and the different combined version of the code. So this is combined with 0, 1, 3, the different optimizations of it. So finally, we verified a full kernel, which is called Asterios. It's a commercial real-time microkernel. And what we try to verify is two properties. The first is absence of runtime error. So what's a runtime error? Is when you have an error in the kernel and then it propagates and it crashes the entire system. And now you have also privilege escalation. So privilege escalation is that when you have an evil task which takes control of the kernel and then the whole system becomes compromised. So what we verified is that we had neither of these two kinds of errors on the complete kernel. And actually we verified two versions. In one version we discovered a privilege escalation vulnerability using our analysis. And in the second version, we proved that such an error was not present. This was fully described in the system conference RCI. So let's move on to the conclusion. So we presented this type-based static analysis, and we think it's very efficient. It's a very amenable to automation. It requires only a few annotations. So I think it's a kind of sweet spot between the precision of the analysis and the number of annotations. It's relatively precise because we can prove memory safety in many programs and light structural invariants. It works on binary code nearly as well on C. And finally, we think it's a robust basis for combination with more advanced memory analysis, which will be able to prove the remaining alarms that we cannot prove yet. So thanks for your attention, and I will be very happy to take your questions.
Thank you, Matthieu. Questions?
From your previous slide, yes, how do you find the remote investigation?
How did we know? We found an error, and then we investigate manually. There was an alarm in the analysis, and when we investigated this particular alarm, we discovered that it was not a false alarm, but it was a true error. So it's I don't remember exactly, but for this error to work, we should have it will require very special conditions where you had a very huge application and managed to point to have a jump. It was a system call which was not properly sanitized, and it could jump to some precise address. And if you put code into that address, then you took control of the entire kernel.
One more question from the audience. The question asks, can you instead use certification with frameworks embedded in corporate Isabel?
Sorry, can you repeat the question?
Can you instead use certification with frameworks embedded in corporate Isabel?
Well, what we perform is automatic memory analysis. So with Coq and Isabel, you can prove such kind of proof, but of course it's entirely manual. So a good question will be, could this kind of proof be used for a complete Isabel or Coq proof? So there are two possibilities. Either we could print some invariants and then attempt to reprove it later, or we can use some certified program analyzer like the one by the concert. I don't remember this name, but there is some certified analysis that provide certified proofs based on this kind of concept. Of course, there are more lengthy to analyze, but in theory, this could be done.
Question?
I would like to ask, what are the types that you need to when you are
from the C code.
Oh, yes. So what kind of annotations are we needed compared to what exists in the C code? So there are different kinds. A lot of them was stating that some pointers may never be null. So this one, okay. Another kind was to relate the size of arrays with values that describe that length. So this was like 80% of what we needed. And almost all of it for the shape benchmark. So for the microkernel, there are different annotations which was related to some page table invariants and so very low invariant on page tables and on the system segments because, well, some kind of thing. So there was also the use of the experiment predicates for this particular invariant. So I think this summarizes on this way.
We have one more question from Victor. So he asked whether you can certify the result of the analysis within pharmacy. Essentially, specify it in pharmacy's language and then check it, for example, with the verification condition checker.
Because pharmacy is a C code analyzer, so we could not certify our analysis with pharmacy, but what we could do is output formal. So there are these CSS specifications that we could output to say that we verified these invariants. So we could output the invariants that we could prove in the CSS specification language, probably. So the CSS specification language does lack separation predicates. I'm not sure how lengthy would such a specification be if we had to print it manually. But in theory, it should be also possible.
Thank you very much. Let's thank Matthieu.